Just going to continue with chapter 24, and then we're supposed to get into chapter 13, according to the syllabus today. But we'll be looking at chemical reactions throughout. And so this is one of the questions they asked earlier. What are the chemical properties of HCl? And so when we bring it down, what are the types of chemical reactions that we're going to look for?
When there's metathesis.
Yeah, so we just need to know, what are the metathesis reactions for HCl? All right, and then what else are there? Acid-base. So look at what types of acid-base reactions. There it goes. And then finally, we got so that pretty much covers all the types of chemical reactions that we're going to encounter. Normally when people think of HCl, the most common answer that they give is that it's a strong acid, but that's not the only property that it has. It can react with other things as well. So metathesis are just favorable ion combinations. So when we think of HCl, and this could be in the gas phase or aqueous phase. Most people think of this, in terms of hydrochloric acid. Hydrochloric acid is going to be a strong electrolyte, and it's going to be E plus and Cl minus. If this were gas phase, we modify it a little bit because in the gas phase, HCl occurs as molecules, and they'll change its physical properties, but chemically it should behave comparably. Well, for metathesis, there are two ions here. There's an H plus ion and the Cl minus. So in terms of metathesis, we look at the cation and see, what kinds of things will H plus react with. And if we think about H plus is automatically, you would think it's a proton that's acid. Acid is H plus. In fact, that's how we identify Bronsted acids. We identify Bronsted acids because all Bronsted acids will have H or H plus, actually H plus. And so typically when an acid has H plus, we write the H at the front. So for example, this will be a little side topic here. Do we write methane as H4C or CH4? We write it CH4 because these hydrogens after the atom that is bonded to are non-acidic. If I were to write it like this, then I'd be assuming that these are acidic hydrogens. This is why, if you look at acetic acid is written HC2H3O2. Why aren't the H's grouped together? I should restate this because so many people, I don't know where they get it. Maybe they Google it, but they might Google it and see C2H4O2, but normally we don't write it. If somebody writes C2H4O2, then a lot of people will think, what are you talking about? What is that? Because there's potential for isomers, so we don't necessarily know. But if somebody wrote HC2H3O2, we would know that is acetic acid. And so there are two different types of hydrogen in acetic acid. The first one is what we call acidic, and the other three are non-acidic. And so what differentiates the first one from the other three? Well, if we look at the structure, we can easily see it. Colin,
how easily you can pluck it off.
Well, yes, it's how easily you can plug it off. And so in order for hydroxide or some water to come and plug it off, it has to have something to grip onto. And so if you're hydroxide, which is like the prototypical strong base, it needs to grab onto the hydrogen. Well, if you're hydroxide, you have a negative charge. You need to grab onto positive charge. Is there much positive charge on these hydrogens bonded to the carbon? No. These are what we call nonpolar bonds. And so the delta plus on these hydrogens is negligible. In fact, a lot of people just ignore it and just call it nonpolar. The range for delta En for nonpolar goes from 0 to about 0.4, 0.5. Delta En is the difference in electronegativity. Whereas this one, the hydrogen has something more to grab onto. Now the bond energies are kind of comparable. A carbon-hydrogen bond and an oxygen-hydrogen bond are somewhat comparable. They're both single bonds. And I think the carbon hydrogen's in the 350 kilojoule per mole range, whereas the oxygen hydrogen bond is actually stronger at 400 plus kilojoules per mole. But even though it has a stronger bond, hydroxide would have something more to grip onto. So if the delta plus is negligible here, just right, the delta plus is negligible here. I mean, it's so small. The delta plus here is significant. And so what we're dealing with is a negative positive attraction. So here, if a hydroxide comes along, it'll have a much easier time pulling on the hydrogen, even though this bond's stronger than the hydrogen over here. In fact, these hydrogens aren't very appealing at all. These would be labeled in what color you're thinking about. If you're a base, you're looking for what color.
Red.
You want red? Well, actually, a good base is more red. So they want, they don't want another red. They want actually blue. And so this hydrogen over here is quite blue in the electrostatic potential map. These hydrogens are more what color? They aren't green. This is acetic acid over. I mean, they aren't blue, sorry. This is a different way of writing acetic acid over here. Let me delete the. This is the condensed structural formula, CH3COOH or CO2H. This is acetic acid. These oxygens aren't bonded to one another. This is the carboxylic acid group here, COOH or CO2H for short. So if you're a base, you're looking for this blue. This is the acidic hydrogen. You aren't going to be attracted to these hydrogens. These hydrogens are green, meaning they're pretty non-acidic. Right? Green is kind of neutral. Red is negative. Blue is positive. Although if you're hydroxide, you'd much prefer this acid. What is this acid over here? Sulfuric. Look how much bluer that is. It can really get a grip on that hydrogen and pluck it off much easier. Even though the oxygen-hydrogen bond here and the oxygen-hydrogen bond here are comparable in terms of bond energy, hydroxide is going to get a much stronger grip onto the hydrogen here. Let's pull it off easier. So this is acid right here, H+. And so what bases does this acid like? Well, this is metathesis. So in metathesis, we're looking at what anions that likes. And so if we're looking at what anions that likes, let's go back to the chart over here, the acid-base chart. So H+ and hydronium are pretty much the same. So if I see hydronium here, that's H+. H+, as you recall, is just a proton. And a proton is extremely reactive because of its small size. A proton is like the nucleus. A nucleus, do you guys recall how much smaller a nucleus is compared to an atom? About how many orders of magnitude?
10,000.
Yeah, 10,000 times smaller. Good. But H plus is a lot easier to write than hydronium. And when you deal with hydronium, you have to add waters to balance things out. And so I'd like to just use H plus. So is H plus strong enough to react with nitrate? So H plus reacts with nitrate. If H plus reacts with nitrate, what forms? Well, if this is the acid, this is the base. So if H plus reacts with nitrate, then we're going to form HNO3. The base is a proton acceptor. We form HNO3. Is that favorable?
No.
No, it's unfavorable because we're going uphill. And also, we're going to form H2O. If we form H2O, then that's also uphill because uphill on the right side is down. And so this is unfavorable energetically. However, what if H plus reacts with trichloroacetate? If H plus reacts with trichloroacetate, this is the base. The base gains a proton from trichloroacetic acid. Is that favorable? Yes, because this is now going downhill. So we're going from a stronger acid to a weaker acid. And over here, we're going from a stronger base, trichloroacetate, to a weaker base, water, in the process of this reaction. And so what this says is that H plus will neutralize any anion or react with any anion, actually, and cation would react with this cation here. Any of these ions here. And so metathesis is favorable ion combinations. We're just looking at ion combinations that are. And so all these will react. And so how should I state that? Well, I'm going to state that is like this. I'm going to state that H plus will react with any ion that is more basic than water. And that covers everything, including the ones that aren't on this chart. And so we just look, if you have a specific ion you're interested in, will it react with fluoride? Yes. It reacts with fluoride to make HI. Will it react with acetate? Yes. It will react with acetate to make acetic acid. Will it react with bicarbonate? Yes. It will form CO2 and water, et cetera, et cetera. Will it react with cyanide? Yes. It will form toxic hydrogen cyanide or hydrocyanic acid. And so here, H plus reacts. Let's see. Okay, I'll go back in here. Doesn't look so good. With all ions, more basic than water. Okay. And so what types of metathesis reactions does chloride undergo? Chloride we have to think. Metathesis is going to involve gas formation. So does chloride combine with any cations to form a gas? You would think it could combine with H plus, but H plus and Cl minus are separate. They don't even come together. They can come together. We're talking. We're not talking about a little bit. A little bit of the H. When you have let's say 6 molar HCl, you can smell it. Have you ever smelled 6 molar HCl? It's really bad for your nose and throat. But what you're smelling is that sometimes an H plus combines with a chloride to make HCl, the molecule. And the HCl, the molecule, escapes from the surface, and you can breathe it in, inhale it. But that's very minor. The vast majority of the HCl stays separate as ions. They don't come together to combine. So yes, it is possible that chloride does combine with H plus to a very small extent to form HCl, but that's very unfavorable. Unless you can drive off the gas. There are ways to make it favorable. Heat it up. If you heat it up, you're going to drive off the HCl to gas. But in terms of metathesis, that's not the type of reaction we're looking at. The type of reaction that we look at is this. Chloride will react with silver ions to form silver chloride. They'll react with lead ions to form lead-2 chloride, and they'll react with mercury-1 ions to form precipitates. Okay. Those are all insoluble. So AgCl, PbCl2, and Hg2Cl2. Those are all precipitates. And that's it for the metathesis. So there's not too much. HCl will react with those cations in solution.
Is there an even better way to say the first one for H plus? Because there are some very few that are ions, like ammonia.
Well, yeah, that's true. You're right. And so what we can say is that reacts with all bases more basic than water. We could say it that way. But there are some bases that are non-electrolytes. Ammonia is a weak electrolyte, so it will form a little bit of hydroxide. And so that's how come it reacts. And so we'll just say that all ions more basic than water. We'll just put a little asterisk there. Because ammonia can participate in metathesis reactions, but these are amines. Maybe we'll talk about it today a little bit here. And then there are other classes. So amines can participate in metathesis. Ammonia and water will react. This is unfavorable, but it's not terrible. And so this is 99.9% of the population stays down here, and this is 0.1%. Actually, it's less. This is greater than 99.9%. This is less than 0.1%. So what we have a situation like this. This is an uphill reaction. And so if we have ammonia and water here, it likes to stay at the bottom of the hill. However, not everybody's the same. There are some ammonia molecules that are very reactive and want to go all the way up here to form ammonium and hydroxide. And this is an equilibrium situation because of the Maxwell-Boltzmann distribution. What was the Maxwell-Boltzmann distribution again?
It's the distribution of the particles and the energies.
Yeah, at a given temperature.
Yeah.
And so not all the ammonias and waters are the same. There's going to be a very small population of very energetic. It's like going on a bike ride. If you're going on a bike ride and you have a big group of people, and we have to climb this hill, not everybody's going to make it up the hill if this is a gigantic hill. You know, just a small subpopulation of that group will make it up to the top, but they don't want to stay there. They're going to come back down. Another group might come back up. And what we're going to end up with is something called a dynamic equilibrium. A dynamic equilibrium is this. The number of people going up the hill is equal to the number of people going down the hill, so the population is stable. The population down here is stable, the population up here is stable, but the number of people going up and down continue. This is just going in a circle here. And so this is what we call a dynamic equilibrium. But the population is small. You know, the bigger the hill, the smaller the population. That eventually the hill gets so big that you expect no population to make it up there. But in this case, for ammonia, we're going to have enough. Now, is that enough to react in a metathesis reaction, this tiny bit of hydroxide that forms? Yes. This is actually enough because hydroxides are so insoluble for a lot of metals.
If that's ammonia with water, what if it was ammonia and hydroxide? Wouldn't that be much more favorable?
Ammonia, yeah, ammonia can attack it directly, or ammonia can, the hydroxide. The hydroxide is a more powerful base. So one thing that can happen is this: if you're an acid, you'll attack this first. As you attack this, you remove some of the population, but the population climbing is still going up. You know, so eventually, what's going to happen is it's going to drive the reaction to the right. That's one way of visualizing this reaction. The other is it can react directly with the ammonia. But we already have ammonia in water. Ammonia in water is already present, and so the hydroxide is present there to react with. This reaction also happens in gas phase. So, for example, it doesn't have to form these. This is just in metathesis. For this. If ammonia reacts in a gas phase reaction, then we can have it react with this. This is a reaction that we do as a demo. We do this reaction where we take HCl gas, ammonia gas. So this is gas phase, this is gas phase. And so what happens here is that the ammonia will attack the hydrogen here, flip it off. So this sp3 lone pair gets pushed into this S and kicks these out. So we end up forming ammonium chloride. Ammonium chloride, when there's no water present, ammonium chloride it's solid. And so it makes it smoke. And the smoke is just tiny crystals of ammonium chloride in the air. This is gas phase, so it can react directly or it can react indirectly to these ions. It probably does both. Ammonia and ammonia-like derivatives. Ammonia-like derivatives are called amines. So we looked at this in Chem 1A. So if you recall, carbon and hydrogen have very similar electronegativities. So what we can do is we can substitute these here. And so this is where R is equal to hydrogen or carbon. You know, and carbon is going to have some other things to it. And so we can have things that are very similar to ammonia. One of them would be something like this, where we'll put these methyl groups on here. And we compare this versus ammonia. And what makes a good base is having a lone pair and having a delta minus. The bigger the negative charge on the base, like hydroxide has a full negative, the better. So let's compare the two delta minuses on the nitrogen here. Would you expect a big difference? We don't expect a big difference because carbon and hydrogen have comparable electronegativities. Okay, then we could look at it deeper. When we look at it deeper, these carbons are actually quite electron rich. The way we determine how electron rich those carbons are is we look at its oxidation state. When we look at the oxidation state here, we think in terms of a tug of war. So let's go ahead and do the oxidation states. Winner take all electrons. So nitrogen versus carbon, if they got in a tug of war, who would win all the electrons? Nitrogen. Carbon versus hydrogen, who would win? Carbon. So carbon ends up with a total of 6 electrons. How many valence electrons does carbon normally have? 4. So it ends up with 2 more than its valence. And so this is a -2 oxidation state. A -2 oxidation state here means it's electron rich, which helps enhance the base strength here even more. So there are competing effects. The competing effects are one, carbon is just a hair more electronegative than hydrogen. It's a 2.5 versus 2.1. So it's going to pull, but then it's got all these hydrogens bonded to it and pull the electron cloud from that as well. And so, well, it pulls it from these. Nitrogen is going to pull it from here. And so this is a pretty good base. This hydrogen over here has 0 electrons. Normally it has 1 valence electron, and so the oxidation state of this is 0, or not 0. Sorry. What is the oxidation state? Plus 1. Plus 1. So this compound here is called trimethylamine, and trimethylamine is as good of a base, perhaps better a base than ammonia. So if we have a hydrocarbon, this is a hydrocarbon group. Then we have an amine. R just stands for the rest of the molecule. And the R's don't have to be the same. In this case, they're all the same. So we have 3 methyl groups there. But they could be 3 different groups. So we signify this by writing R prime, R double prime, R triple prime, meaning that they don't have to be the same. They can be the same, but they don't have to be the same. So in other words, I could throw an ethyl group there, like I have a dimethyl ethyl amine, or 2 ethyl groups, methyl, or actually diethyl methylamine, something like that. How about this? How about this one? Is this trifluoroamine? No, we don't call that trifluoroamine. We call that nitrogen trifluoride. I suppose you could call it trifluoroamine, but that wouldn't quite be right. But there's something quite different about this. This is not ammonia-like at all. Why?
Because with ammonia, the nitrogen wins and the hydrogen, but in this one, the fluorines are going to win.
Yeah, the fluorines are going to win. That means nitrogen is going to be delta plus, not delta minus. And there's going to be a huge shift in the oxidation state. So nitrogen wins all these electrons here against carbon. Nitrogen versus carbon, nitrogen wins everything. So how many electrons does nitrogen end up with? 8. How many does it normally have? 5. So it has 3 extra electrons, which gives it a -3. -3 is electron rich for nitrogen. I talked about the oxidation state. Varied. Nitrogen normally has 5 valence electrons. And so there are 2 choices. One, it can get an octet at 8 electrons and be like fluorine, or not saying neon, be like neon. Or 2, it can lose 3 electrons to go to 2 electrons to be like helium. And so nitrogen is either going to want to try to be like neon or want to either be like helium. If it actually, I shouldn't say 2. You have to be very careful here because we have total electrons versus valence electrons. Helium is tricky because that's in another shell. So I'll probably do total electrons here. So let me just cancel this out. We're going to look at total electrons. Nitrogen has 7 total electrons. Neon has 10 total electrons, and helium has 2 total electrons. So if it wants to be isoelectronic with neon, how many electrons does it have to gain? 3. So if it gains 3 electrons, then that's -3 oxidation state. Or if it wants to be like helium, how many electrons does it have to lose? 5. So it's going to be -5 electrons. So that's going to be +5 oxidation state because it's the smallest 5 electrons. And so this is the limit. So when nitrogen's at -3, I call it electron rich. What is nitrogen over here? Okay, so let's go ahead. fluorine versus nitrogen, fluorine wins. And that leaves it with its two lone pair electrons. You're supposed to have how many valence electrons? 5 valence, so it's plus 3. Plus 3 is on the electron poor side. So do you see these nitrogens are dramatically different, whereas these nitrogens are quite similar? And therefore, this is going to behave quite differently. Would you expect this to be a good electron pair donor? No. Because it's already positive. Why would it want to give up more electron density by sharing? Does that make sense? No? In other words, what makes a good donor is having lots of negative charge density, negative charge cloud. And then it's more willing to donate an electron because when it donates electron, it's giving up one electron. It has two, but it's giving up one to the other atom. It's forming a coordinate covalent or dative bond. This is why fluorine will not form those coordinate covalent bonds. Fluorine doesn't want to donate. All right, these are amines here. So, since metathesis, speaking in strictly the metathesis sense, we're just looking at ions. And so we look at this first one. Amines are all weak bases. This is a class of organic compounds. These are weak organic bases. That are ammonia derivatives. There are a lot of drugs that are amines. A lot. One of them is the hydroxychloroquine. That's gotten a lot of press lately. The way hydroxychloroquine is supposed to work is it gets into the cell and then changes the pH inside the cell. When you change the pH, it tends to screw things up, like hydrogen bonding interactions and that type of stuff. It disables things. But cocaine is an amine, and a lot of antibiotics are amines. So we'll look at the amines and metathesis a little bit. All right, let's take a look at acid base. So this is it for metathesis and react with this. For acid base, we're going to say kind of the same thing here. H plus is an acid. Okay, and in this case, I'm just going to say reacts with all bases. Stronger than water. Chloride is a base, but we have to put a little asterisk here because how good of a base is chloride? It's a horrible base. We just say it's too weak. Too weak. Therefore, we just call it like neutral. It's not going to neutralize anything. It's, in that sense, that's what I mean by neutral. Water is also neutral, but water can neutralize acids or not react with acids and can react with bases.
Would it be correct to say that chloride would react with all acids stronger than H2O outside of water?
In the gas phase. If we go back to this chart, how do we rank these if we have a leveling effect? the leveling effect says all these are equivalent. So how did they tell? Well, one way they could tell is how easy is it to pluck the hydrogen off. You know? And then typically that would be in the gas phase. So if there's no water around and we're dealing with molecules of these, then you can determine it. And so if this were gas phase, then you'd expect it to react with these species, to form a gas. But in aqueous solution, it's not going to happen. And since we're dealing mainly with aqueous solutions, it's going to ignore it. But, okay. The solvent, like water, plays an important role in chemical reactivity. Water is the most common solvent, but in organic chemistry, you deal with lots of different solvents. And sometimes you have to be very selective about what solvent you use in order to get the reaction that you want. And so it gets more complex. And so chloride, we don't even consider it a base. Okay, then we go on to redox. What types of redox reactions do we have? And so for redox, we'll just look at the species here. We have H+. H+ is an oxidizer that occurs on the left side of the chart. And so let's take a look at the chart here. You see H+ is an oxidizer. Like, for example, what can H+ oxidize? So we looked at this. Can H+ oxidize copper? Yeah. So if H+ tried to attack copper, then the copper would be converted to copper 2+. Is that uphill or downhill? Going from H+ to copper 2+. That's uphill. That's not downhill. And then copper would be replaced by hydrogen. Well, that's uphill as well. So that's not uphill. But what about, will H+ attack iron? Is there any problem with that? No, because if H+ attacks iron, then the iron gets converted into iron 2. That's downhill. H+ going to iron 2. And then iron will be replaced by hydrogen, and that's also downhill. Because the H+ will be converted into hydrogen. So this is the zigzag pattern that we use here. And so that means H+ will react with anything downhill over here. And so how should we frame that? Well, this list is not comprehensive, so we should frame it how? How should we state that?
H+ will react with all reducers stronger than hydrogen.
Yes. H+ will react with all reducers stronger than H2. Put that here. So this is an oxidizer. This is acid. This is oxidizer, reacts with all reducers. Stronger than H2. Okay, and then we could just pick, or we could list them. For example, this. How about chloride? Does chloride occur on the side? Do you see chloride on the chart? Yeah. Chloride occurs on the chart right here. Meaning that chloride is a oxidizer or reducer? Chloride's a reducer. So what types of things will chloride react with? So let's try this. Will chloride react with bromine? So if chloride reacts with bromine, what forms? So chloride reacts with bromine, chloride gets converted into chlorine. So we're going to react with bromine, bromine is going to get converted to bromide. The chloride gets converted into chlorine. So we're going to start with bromine and replace it with chlorine. Is that downhill or is that uphill?
Okay.
That's uphill. And then chloride is going to be replaced with bromide. This is also uphill on the right side. So that's not favorable. Instead, what if chloride reacts with chloride and react it with let's try to react it with permanganate, an acid. Here. So chloride reacts with permanganate in acid. If chloride reacts with permanganate in acid, what forms? Well, the chloride is going to get converted into chlorine. And the permanganate in acid is going to get converted into Mn2 plus in water. So what we're going to do is we're going to go from permanganate to chlorine. Is that downhill or uphill? That's downhill. And so that's favorable. And then the chloride is going to get replaced with manganese 2 plus. That's also downhill on the right side. We're going up. So that's favorable. So how should we state this in terms of chemical properties then? We should say that chloride will react with, yes. Chloride will react with all oxidizers stronger than chlorine. Well, there aren't a whole bunch. Chlorine already is a powerful oxidizer, but we need an even more powerful oxidizer to strip it. Remember, chlorine versus chlorine is going to result in a tie, so we need something stronger than chlorine to strip the electron off. And so what's stronger than chlorine? Fluorine, ozone and acid, this weird thing here, there's a peroxide, another peroxide, manganate, another peroxide and acid. But there are more. There are more because we aren't looking at all of them. We're just looking at what's on this chart. So this is a reducer. We'll just say reducer. And this reducer reacts with all oxidizers stronger than chlorine. So that's it. Uh-huh.
So on an exam or a quiz, the way you would give this question and the way you would answer is like
It's like this, something like this. You can format it differently, however you want to format it. In fact, we'll have a quiz right now. This is worth 5 points. You can tell me the exact same thing, except tell me the chemical properties for nitric acid. This is an open book, open notes. You can work with other people if you want. If you want to try it. So we'll just do the same thing, except in this case, we'll just ask, what are the chemical properties of nitric acid, HNO3?
it's kind of the same as HCl. It's normally we expect everyone say these are all percentage. So it's two weeks and that's these are all smaller.
All right, so that was good for the nitric acid. But, well, let me just make a comment about HCl. You know, they're both strong acids, HCl and nitric acid. HCl is a little bit more reactive in terms of metathesis, right? So I have silver ions, lead ions, mercury 1 ions. HCl is going to react, whereas HNO3 won't react with silver, lead, or mercury, or any other cations. And so HCl is a little bit more reactive in terms of metathesis. So metathesis, we got to watch out for HCl if we don't want it. If we want a metathesis, then of course we can use HCl, no problem. Nitric acid is unreactive in metathesis, but it is reactive in redox. And so we got to watch out when we use nitric acid. And therefore, you know, both of them are oxidizers, you know, because both contain H+, but nitric acid is a more powerful oxidizer. And therefore, we kind of label nitric acid as belonging to a class of acids called the oxidizing acids. Why call it an oxidizing acid? Because all acids are oxidizers. All acids have H+. Even weak acids are oxidizers. And the reason we call them oxidizing acids is because they're stronger than your typical acid. And the typical acid would be like HCl. HCl is your typical acid. That would be called a mineral acid versus an oxidizing acid. Well, anyway, one of the properties of chloride is that it precipitates a silver chloride in the presence of silver ions. And so the nitrate is the spectator. We don't want it to do anything. We just want the silver ions to react here. This is why nitrates also good. Nitrates are typically spectators in metathesis reactions. And so we precipitate out 3 silver chlorides, 3 silver chlorides. That's what we expect because both of these dissociate with the ions and the ammonia break free. But that's not what was observed here. When we have the penta ammonia, or mean, sometimes we call it a mean, and then we only form 2 moles of silver chloride. So why is that? And the reason is because the ammonias aren't just stuck in the crystal lattice. The ammonias actually bond. And this is actually a Lewis acid-base reaction. The Lewis base is ammonia, Lewis acid is cobalt. Normally, when we share an electron pair, nitrogen will donate 1 electron to cobalt and keep 1 electron for itself. And so this can change the formal charge, whereas before, both electrons belong to nitrogen. And so we expect changes in charge. So for example, since cobalt's gaining an extra electron, it should go from +3 to +2. And since nitrogen's losing one of its electrons, it should go from 0 to +1. But for these complexes, it's weird. We don't count the electrons like we normally count. And so we don't bother with formal charge. This is why I cross out formal charge there. Not only that, we'll see that VSEPR doesn't apply in the VSEPR is, you know, how many bonding pairs, how many lone pairs does it have. It applies here. I mean, this is going to be tetrahedral over here. This is trigonal pyramidal. But it doesn't apply in certain structures. It appears to apply, but it doesn't. And so this is 1. But the cobalt's still there. How many ammonias do you think can attack? Just 1? If there's more ammonias that want to attack cobalt, how many do you think we can fit around cobalt? 3, 4, 5?
I think 6.
It's actually 6. And so what we end up with is a structure that looks like this. These are all coordinate covalent bonds. This is incorrect. We don't show the lone pair and a bonding pair. You see a lone pair and a bonding pair shown? It's too many electrons. It doesn't have that many electrons. And so this drawing from our book is not really accurate. And so let's redraw this more accurately. So we'll just have another ammonia come and attack the cobalt-3. We'll have a total of 6 come, and that's about as many as we can fit around this. And so we'll throw in a cobalt in the center. And the cobalt, weirdly, is still going to stay 3+, regardless. And if we put in 6 here, it's going to be in an octahedral. We can use wedge dash to show that if we want. So if I show this by a wedge dash, then I'll wedge out these ones here, and I'll dash in these ones. And so it forms an octahedral structure. Then the ammonia's come and bond in here with the lone pair. So now the lone pair is gone because the lone pair was used to make the coordinate covalent or data bond. Now the nitrogen's bonding here, so what I'm going to do is I'm going to write these ammonias backwards. This is not to say it's a triprotic acid. It's just to show that nitrogen's bonding. Now, these bonds are covalent bonds. And they're the coordinate covalent or the data bond. Just to emphasize that both bonding electrons. But once a bond forms, you can't tell, which electron came from nitrogen, which electron came from. Actually, both came from nitrogen, but you can't really tell. It's just like any other covalent bond. Now, if we have a molecular species, do molecules ionize? Like, for example, remember when we think of strong electrolytes, weak electrolytes, and non-electrolytes. Non-electrolytes are molecular compounds that phenol, methanol, those types of things. And so here, when we think about this, what happens is this thing does not ionize. This thing kind of stays together in water. And this forms a gigantic cation. And so the charge here, this is the oxidation state of the formal charge. This is the net charge out here. This is 3 plus. We add up all the formal charges or all the oxidation states and we get this. Yeah. And this is called a complex ion. And so the bases are more or less strongly bonded to the acid here. So this is our base. This is our acid. But in these complexes, we do these different names. For example, the base here is called a ligand. Ligands are Lewis bases that attack these metals. And this acid here is the central metal. The central metal, oddly enough, it doesn't even have to have a positive charge. We could have neutral metal atoms being attacked by Lewis bases. And they also come by charge. So this is the oxidation state. And so when we name this complex ion, the name for this complex ion is going to be called hexaamine. Now, hexaamine would have a double vowel. It would be HEXAA. But sometimes what we do is we eliminate one of the vowels to make it sound a bit smoother. And we have 2 amines as far as spelling goes. Amine with 2 M's is ammonia as a base. And so if we have a double M, that's ammonia. Versus amine with 1 M is what we call the weak organic base, a class of weak organic bases. And so you have to keep note, 2 M's, this implies we have ammonia. 1 M means we have a class of ammonia-like bases. ammonia-like bases. And the name for this goes on. It's hexamine cobalt, and this is all one word. There's no space here. Hexamine cobalt, and then we have a Roman numeral 3 to indicate the charge on the cobalt. And so the metal there is written on it. So this is the cation. What is the anion here? So the anion, let's make those in red here. We have a 3+ cation, so we'll need 3 chlorides. Let's put one there, one here. This is going to be in some three-dimensional lattice. And we're going to throw out one over here. Now, in an ionic lattice, it just spreads out in 3 dimensions. So this is going to be just alternating. So this is solid. And so what we call this is hexamine cobalt 3 and the anion, it's an ionic compound. And so we're going to call it hexamine cobalt 3 chloride. So hexamine cobalt 3, this is our cation, and chlorides are anion. And so we named this as an ionic compound. So what happens is chlorides are soluble, except for silver, lead, and mercury. So if we take this chloride salt and dissolve it in water, then what's going to happen? Well, when we take this, we're going to get the hexamine cobalt. These are going to stay intact. The ammonias aren't going to break off, interestingly enough. And so the ammonias stay on, and we end up with this as our 3+. And so this would be aqueous. And then we're going to have the 3 chlorides. Aqueous. So maybe I should do chlorides. Consistent. All right, so these are going to be independent ions. So the hexamine cobalt 3 ions are going to be floating in the water, or, there's going to be some diffusion through water molecules, and the same thing with the chloride here. Now, we talk about certain things here. So, for example, there's something called the coordination number. The coordination number on cobalt means how many things is it bonded to. And the coordination number on cobalt is 6, because of the 6 bonds. That's about the max. We could try to fit a 7th on there, but it's not going to fit. It's got a max coordination number of 6 here.
If there was a lone pair, would it count towards the coordination number?
Yes. If there's a lone pair there, it would count towards the coordination number. How many valence electrons does cobalt have? So first we'll look at cobalt. Tell me how many valence electrons cobalt has. Well, let's look at the electron configuration for cobalt. Electron configuration for cobalt is going to be argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 3d7. Is that right? Yeah. 4s2, 3d1, 2, 3, 4, 5, 6, 7. Yeah, that's right. How many valence electrons is that?
I kind of forgot the rules for this, but I want to say 7.
No, not 7.
Is it 2?
It's 2. So oftentimes we'll write it differently. So typically this is written argon 3d7, 4s2. Why only 2? Why not 9?
The other 7 are on the 3 orbital.
Yeah, they're what we call the inner shell electrons, right? And so the outermost shell is going to be 4s2, so it's 2 valence electrons. So in cobalt 3 plus, we lose all 2 valence electrons plus one of the inner electrons. And so in cobalt plus 3, the electron configuration is going to be argon 3d6. So how many lone pairs should I write on cobalt? Combination number. I have 6 3d6. Shouldn't that be 3 lone pairs to count for the 6d electrons?
You have 1 lone pair, and then
Okay, where should I put the lone pair
I don't think that, I don't think it has any of that. There's no room for that, right?
here? Yeah. I mean, there's really, what orbitals would you use? Remember in valence bond theory, we had different hybridization. If you have octahedral like this, what's the hybridization of that? I didn't really do much because it's not entirely correct, but it's sp3d2 hybrid orbitals. You guys remember sp3d2? I didn't talk about it much because it turns out it may not be correct. But anyway, we have these. It turns out these d6 electrons are what we call non-bonding. These are like cool inner shell electrons. These ones are non-bonding. So these ones are inside. They don't participate in the bonding. And so we don't write any lone pairs here. And since complexes are a bit tricky, this is the easiest thing to do. Ignore Vesper. You know, how many lone pairs, how many bonding pairs. Ignore formal charge, that kind of stuff. Don't worry about the number of electron pairs on the central metal because there aren't any. When we do unless it's neutral, when we have a central metal cation, what are the 2 most common charges for cobalt? Plus 2, plus 3. Well, when we have a cobalt as an ion, it's not going to have any valence electrons, so we don't write any lone pairs there. And so don't think about this too much. I know a lot of people want to be very thorough, but I'm not going to be. We don't think of this as being sp3d2 at all. And we don't use Vesper to dictate it. In fact, it's very tricky to determine. If we have 6 bonding pairs, we expect octahedral, right? What if we have 4 bonding pairs and no lone pairs? If we have 4 bonding pairs, we expect it to be tetrahedral. Vesper says tetrahedral. But this has 4 bonding pairs and no lone pairs. You know, we could get this square planar if we had two lone pairs. The lone pair sitting on top and the lone pair sitting on the bottom. It'd be octahedral with a square planar molecular geometry. But no, there are no lone pairs here, yet it's square planar. So there's something else going on with this structurally. We'll talk more about this. But it's hard to predict. And why don't we fit 6 things? Like, look at the zinc. We only have 4. Why didn't we fit 6 around it? And then silver, isn't there a lot more room on silver? This only has 2. Why don't we put 6 ammonias on silver? We should put 6 ammonias on everything. But this is the observations. The observation is silver only has 2. This is the coordination number, so it only can form 2 bonds. Platinum depends if you're looking at platinum 2 or platinum 4. If we're looking at platinum 2, then its coordination number is 4. But if it has a coordination number 4, it could be square planar or it could be tetrahedral. You know, as far as the scientific method goes, tell me what we should do when we look at complexes. Did he come up with a question, or did he start with an observation? On an observation, the observation was, hey, this doesn't look right. You know, there's something wrong with this. And the same thing here. You know, when we look at these when we look at these coordination numbers, did you already predict this? Did you already have a question about these coordination numbers? No, we're just looking at, these are the coordination numbers observed in nature. And then we're going to see if there's any pattern to it. Maybe there's a pattern to it. All right, we're out of time, so I'm going to continue chapter 24 next week. So it's just slightly behind schedule here. And so I'm thinking, just work on the reactions homework, you know, and then start reading chapter 24. Okay.
Does it only have a due date? Do you time a date?
Yeah, on the day of the test. We're going to have a test.